Having looked at the pancreatic acinar cells and the pancreatic duct cells, let's have a look at the overall pancreatic juice composition that we've made so far. Well, the acinar cells, they've made these zymogens, which are protein enzyme precursors. They've secreted the sodium chloride for hydration and the pancreatic lipases. And the duct cells have modified these protein secretions by secreting water and bicarbonate through this chloride bicarbonate exchanger mechanism. So all this makes pancreatic juice. So overall, what is the pancreatic juice? Well, it's inactive zymogens and some digestive enzymes. But if you remember, I also mentioned these goblet cells. They line the ducts also. Goblet cells secrete mucus, and the mucus is for lubrication, which is / hydration. It's for protection of the epithelial cells, and the goblet cells also, they bind to pathogens. And this allows, and then once they've bound to pathogens, they interact with immune cells for the immune function to prevent pancreatic infections. So in terms of fed and fasted states, the pancreatic secretion and rate of secretion, as well as the composition, it changes. It increases in the fasted state. There's overall, when you've eaten, there's going to be more bicarbonate and less chloride, because remember, the chloride is going back into the duct cell via the chloride exchanger, and the bicarbonate is coming out of the duct cell. So in the fed state, you're going to have a less chloride and more bicarbonate. So let's have a look at that. So in the fasted state, you'll have low level release of the pancreatic enzymes. That's the fasted state. Whereas in the fed state, well, what happens? Well, you'll have motility, increased motility, like peristalsis to get the food to move, increased gastric secretions as we've looked at in the stomach. And in the pancreas, the pancreatic secretions will increase by 20 times. And what will this result in? Like, as we've said, high bicarbonate and low calcium, low chloride even, due to the chloride bicarbonate exchanger in the duct cells, which, if you remember, is affected by the CFTR channel is affected by cystic fibrosis, which prevents the duct cell secretions. So what inhibits the pancreatic cells? Well, we've looked at what stimulates them: secretin, acetylcholine, cholecystokinin, and VIP. And if you recall back to the lecture on the stomach, the thing that inhibits the secretion of acid is somatostatin from D cells. So somatostatin is also the main inhibitor of pancreatic secretions. So pancreatic D cells, they produce somatostatin. The way they inhibit the pancreas is essentially two mechanisms. They inhibit the I cells from producing cholecystokinin. And if you remember, cholecystokinin is the thing that stimulates the pancreatic acinar cells. So if you inhibit that I cell to the less cholecystokinin, you won't be able to get acinar cell stimulation. But also, the thing that stimulates the pancreatic duct cells is secretin. You can remember that by secretin causing the duct cells to secrete their bicarbonate, right? So if somatostatin inhibits the pancreatic, the S cells, the duodenal S cells, from producing secretin, and you get less secretin, you're not going to be able to get duct cell stimulation. So let's have a look at that. So the pancreatic D cells have produced somatostatin. It does two things. It's inhibited the I cells from producing cholecystokinin, and it's inhibited the S cells from producing secretin. So you won't get acinar cell stimulation from the cholecystokinin, which acinar cells produce the lipases and zymogens, and you won't get duct cell stimulation to produce that bicarbonate and water. And you can also, another way of inhibiting the pancreatic secretions is by using a somatostatin analog. So this is another chemical that has the same effect as somatostatin. So this is called octreotide. So the somatostatin analog, octreotide, essentially does the same thing, inhibits the I cells and S cells, ultimately causing less pancreatic secretions. So now if we have a look at the phases of pancreatic secretions, well, as I mentioned, the pancreatic acinar cells are constitutively active through the PKC pathway, so they're always producing like a basal level of pancreatic secretions. But there's also three phases during when you're eating that cause an increase in pancreatic secretions, which can increase up to 20 times, as I mentioned at the top there. So first of all, we have the cephalic phase, and cephalic is always to do with nervous stimulation. So what the cephalic phase is the site taste, and smell of food causes vagal stimulation, releasing acetylcholine. This causes 25% of the pancreatic secretions. This is the cephalic phase. And then what happens is, well, because you've made the pancreatic zymogens, you've released the pancreatic zymogens, which are precursors for protein enzymes, these amino acids get released from digestion. And if you recall back to, if you remember that fat can be associated with I cells, whereas protein can be associated with G cells. So the products of protein digestion, amino acids, they stimulate the G cells to produce gastrin. Now, gastrin, if you remember, it acts on the, what does gastrin do? Well, gastrin stimulates gastrin stimulates parietal cells of the stomach to secrete acid. It stimulates parietal cells indirectly by acting on ECL cells to release histamine, which then acts on the parietal cells. And the way gastrin works is, well, it's a weak CCK agonist. It acts on the CCKB receptor. So therefore, if gastrin is a weak CCK agonist, then, and remember CCK is cholecystokinin, and cholecystokinin stimulates pancreatic secretions. So if gastrin is released, it's also going to cause some pancreatic acinar cell stimulation. So that's the products of protein digestion, stimulating G cells to produce gastrin, which is a weak CCK agonist, causing low level of pancreatic secretions. But also in the gastric phase, once the foods enter the stomach, you also have stomach distension. So the stomach will be expanded because it's full of food. And stomach distension, what that does is it causes a vagovagal, which means vagus to vagus, gastro-pancreatic reflex, so the stomach to pancreas reflex. And this releases acetylcholine because it's vagus. And acetylcholine, if you recall, is another one of the stimulants, along with cholecystokinin, of the acinar cells. So this causes a low level, 10 to 20% of pancreatic secretions. So food is entered. First of all, you've seen the food, that's caused some secretion, which is in the cephalic phase. The food has then entered the stomach, which causes the gastric phase, and the products of protein digestion and gastric distension have stimulated some pancreatic secretions. But then the next phase, if you think about it, once the food's gone from the stomach, what's going to happen next? It's going to enter the duodenum, so it's going to enter the intestines. So this is called the intestinal phase. And in the intestinal phase, if you think about it like this, the chyme, it enters the small bowel. And what's in the chyme? Well, the chyme has gastric acid from the stomach. And gastric acid, what that does is because it's acidic, you want less bicarbonate. You want more bicarbonate secretion, don't you, to neutralize the acid. So what it does is the gastric acid stimulates duodenal S cells to secrete secretin. And if you remember, secretin stimulates duct cells to release bicarbonate by causing the opening of the CFTR channel. So chloride can leave the cell, and when the chloride enters the cell, the duct cell back through the chloride bicarbonate exchanger, the bicarbonate is secreted. So that's the gastric acid in the chyme. But also the chyme also has lipids, right? So the lipids, what they do two things. Remember, fats stimulate I cells to release cholecystokinin. The cholecystokinin stimulates the acinar cells to release their secretions. And also, because the food has entered the intestines, it causes another reflex. It causes the vagovagal, so vagus to vagus, entero-pancreatic reflex. This intestines to pancreas reflex. So we had the gastropancreatic reflex, and when the food enters the intestines, it causes the enteropancreatic reflex. And this will be, the acinar cells will be even more active if you have a high-fat diet, which makes sense. You have high fat, you want more lipases to break down this fat. So in the intestinal phase, what's happened when the food's entered the small bowel? The gastric acid has caused bicarbonate secretion through S cells, and the lipids has caused lipase and zymogen secretion through the I cells and the vagovagal enteropancreatic reflex. And this is the intestinal phase, which accounts for 50 to 80% of the pancreatic secretions overall.